So here's a video for you to take a look at some of the different types of reactions. For a while, we've been talking about these double replacement reactions. There are two types of those. Here's our four other general types of reactions, which can also be reduction reactions, often called redox reactions. So as you're going to go through this video, I'm going to show some examples and then give you an opportunity to practice. So you're probably going to want to have a periodic table and piece of paper and pencil handy so that you can pause the video and practice these things. All right, so don't forget double replacement reactions look like you see right up here. So your reactants are two compounds and your products are two different compounds. Generally, these are all ionic compounds, and so the reactants switch partners. Also, the products, one of them is going to be insoluble, and so we tell that with an S. All right, and to figure out which one is going to be a solid, insoluble, we simply use this chart right here that tells us, like for example, this one, calcium carbonate. So here's calcium, here's carbonate, and you can see that where they meet at that intersection, it is a solid. So calcium carbonate would be our solid that settles to the bottom, our precipitate. And so as we're taking a look at these double replacement reactions, what we're going to want to be able to do is separate them out into the ions that make them up. And so let's go ahead and practice doing that with this equation right here. So sodium chloride reacts with silver nitrate to form solid silver chloride and sodium nitrate. And so we're going to separate each one of these into the ions. So instead of saying NaCl, we're going to say Na, that is the ion, Na plus 1 and Cl minus 1, and right on along. So we're going to go through each of those to do that, except for the AgCl, because this is our solid precipitate. And so we're going to be taking a look at what ions do we need to get to that solid precipitate. We're going to need silver, and we're going to need chloride to get to that solid precipitate. These other ions that are left floating around in there, that's just what they're doing. They are called our spectator ions. So we are not really going to need them. So we're going to cross those out. And so when we write the what's called the net ionic equation, it's going to give just those ions that result in our solid precipitate. All right, are you ready to practice one? Let's give it a go. Actually, I've got two here for you to practice. All right, so here we've got magnesium chloride reacting with carbonic acid, hydrogen carbonate to form magnesium carbonate and hydrochloric acid or hydrogen chloride. All right, so how did you do? Did you figure out all of those ions that would give you magnesium, the solid precipitate, magnesium carbonate? Now, do we need magnesium? Yes, we do. Do we need chloride? No, that would be a spectator. Do we need hydrogen? No, that's a spectator. The other one we need is this carbonate. So you can see these spectator ions are present in the reactants and, of course, in the products. And so our net ionic equation would look like this. All right, let's go ahead and try the next one. All right, so how did you do? Did you separate them into the ions, leading up to our copper 2 hydroxide? And then figure out what our net ionic equation is, and there it is right there. So we can actually cross out all of these spectators. They would not be needed. Another type of double replacement reaction is an acid-base reaction. And so remember in that acid-base reaction, we're getting an acid reacting with a base. The way you can tell an acid is because it's always going to have hydrogen, or almost always going to have hydrogen that it's able to donate. Hydroxide is one of our indicators of a base. It's not the only one, and we will talk about that when we talk about bases. And our products are salt and water. So take a moment and see if you can do the next one. Oh, so here is our acid. Here is our base. Of course, it doesn't have hydroxide, of course, after I just said that. Here is our salt. And of course, here is water. We're also getting some carbon dioxide gas. So if we did this reaction, we would see some bubbles. Another type of reaction is our oxidation reduction reaction, affectionately called redox. These occur in pairs, and again, they're based on the movement of the electrons. Oil rig is the little acronym that we can use to remember that, where each letter stands for something. So oil, oxidation is loss. So when an electron is lost, which we know metals like to do, that would be oxidation. Rig is reduction is gain. So when they gain electrons, that would be, we would say that they were reduced. And so just again, another easy, good way to remember that. And so what you've got to be able to do is look at the periodic table and remember what those ions are. So hydrogen is generally going to be a +1 if it's bonded to a non-metal. If it's bonding to a metal, it can also be a -1. Oxygen is almost always a -2. And the rest of the ions go with their groups as they're arranged. So let's practice seeing if you can figure out the oxidation numbers for some of these. Remember that elements by themselves have oxidation number of 0. So that is important to remember. All right, so let's take a look at this first one. So I know, of course, so what I'm going to be asking you for the first one is to see if you can figure out what N is. What would be the charge or the oxidation number for nitrogen? Hopefully you said, hold on. Oh, I thought I had it in there, and I do. I'm sorry. +5 for nitrogen. So that way it's going to equal 0, because 3 of these O2 minuses, this is going to be a 6 minus. And so that nitrogen has to equal out. All right, and so in this one, I'm going to ask you to find Mn. So hopefully you said something like this with a 7+, because again, as we have these 4 O's that are each a 2 minus, that's going to be an 8 minus charge. Then we've got our potassium, which is +1 because it's a group 1 metal, to give us Mn with a +7. All right, and so here's a great time for you to practice these. We've got a redox reaction for you right here. See what you can do. And you didn't even need those polyatomic ions, so hopefully you came up with this reaction right here. We've got iron 3 chloride, and I'm just checking to see, it's not quite balanced yet. Hopefully I have some more coefficients in there, but I don't. So we can take a look at that. So we're going to need those coefficients right there. And so right here, iron is a 0 charge. Here, iron is going to be a 3+ charge. So our iron goes from a 0 charge to a 3+ charge, whereas our chlorine goes from a 0 charge to a -1 charge. So who's oxidized? Who's reduced? Of course, iron is oxidized in this case, and chlorine is reduced. Here's another one for you to practice and a great time to stop the video and see what you can do. All right, so taking a look at each one, how are we going to do that? Hopefully first you determine the oxidation numbers of each chemical species. Then you looked at what was being reduced, like by charge. Remember, reduction is gain. So when these chemical species are gaining electrons, they're becoming more negative. And then what was oxidized? Oxidation is loss. So when they're losing electrons, they're becoming more positive. And then, of course, there can also be spectators in this type of reaction as well. So what did you say? Did you figure out NO3, of course, is a -1, as we already know. That's zinc. That should be for zinc right here. Sorry, I'm a little bit off. And hopefully you came up with that iron is a 3+. Now, how am I coming up with this? Well, I'm just uncrossing that and figuring out the charge that iron was at the beginning. Just like that. And then I'm figuring out what are the charges or the oxidation states of my ions at the end. Of course, nitrate is going to be still that -1. There's iron, that's a 2+. And so what has happened to the charge of my iron? It has been reduced. So we went from 3+ to 2+, so that was reduced, whereas zinc went from 0 to 2+, and so zinc was oxidized. And so how did you do with that? Hopefully you did well with this reaction. And of course, as you know, then we are into the moles. So we're measuring quantities of chemicals, which you're doing very well with. I hope this helps you.